Hi everyone, welcome back. In this section we're going to look at the chain rule for multivariable functions. So this is an extension of the chain rule for functions of a single variable that we studied back in Calculus 1, and just like that chain rule, it's about a composition of functions. So we've got an outer function and some inner functions, and we want to work out what the derivative is of the composition by working out the individual derivatives of the component functions and then piecing them together. The piecing them together is known as the chain rule. So before we get into that, let's have a look at a particular example. Now this example is a related rates problem from Calculus 1, one that we've done a bunch of when we studied Calculus 1. So the idea is we've got sand that's being poured on top of a pile, and as it's getting poured on top it forms the shape of a cone. This cone has some base radius r and some height h, both of which are changing over time. And we're interested in how the volume changes in time. So let's work out what the volume is first. The volume of a cone is 1/3 pi times the base radius squared times h. And here we are thinking where r and h are functions of time t. And so we're given at a particular moment in time where the base radius, the height is 5, the base radius is 2, and we're also given the rates of change in the height and the radius. We want to know what the rate of change in the volume is at that time. How is the volume increasing at that particular moment? So in order to do that, we need to come up with a relationship between the rate of change in the volume and the rates of change of the two variables that the volume is a function of. And so we need to differentiate with respect to t. So here we look at this and we say, well, this is a product. It's a product of an r squared and an h with a constant up front. But r and h are both functions of time. So I'm going to use the product rule, and then I'm going to have to use the one-dimensional chain rule, the chain rule from Calculus 1, because when I differentiate, for example, the r squared, it becomes 2r times the derivative of the inside function, which is dr dt. So we'll go ahead and we'll work out the derivative. So using the product rule, it's the derivative of the first function, the r squared. That becomes the 2/3 pi r. And then there's the h there, dr dt. And then we're going to add to that the first function, 1/3 pi r squared, times the derivative of the second function, dh dt. So this is by the product rule. Alright, so now we've got a relationship between the rates of change. We're interested in precisely the moment when the h value, the height is 5, the radius is 2, the height is changing, it says increasing at a rate of 0.4, so that's positive 0.4, and the base radius is changing at a rate of 0.7. It's increasing at 0.7 meters per minute. So those are positive quantities. So for these values of our variables, we can go ahead and pop those into our equation, which relates our rates of change. And we get that the volume is changing at a rate of 2/3 pi times 2 times h, which is 5, times dh dt, which is 0.4, plus 1/3 pi r squared, which is 0.7 squared, times dh dt, which is 0.4. And whatever that value works out to be, that's cubic meters per minute. So it wasn't the fact that we're going through a related rates problem that's important here. This is where I want to draw your attention to. So we did a derivative. So let's have a look at that derivative stage. We did a derivative. So we differentiated this expression, v, with respect to t. So we're thinking of v, it's a function of r and h, but r and h are both functions of t. But I can take a look here as to what these pieces are. So what is that piece? And what is that piece? Now that we're used to seeing functions of multiple variables and partial derivatives, maybe we can interpret these as some partial derivatives. And the idea is absolutely we can. It looks like this first piece is just the partial derivative of v with respect to r. whereas the second piece is the partial derivative of v with respect to h. I'll clean that one up a little bit because I didn't write it very clearly. So that's the partial derivative with respect to h. So it looks like when we did the derivative here, although when we did it, we just used techniques from Calculus 1, product rule. I've indicated that here. It's the product rule. And we thought of these as functions of t. But if I take a step back and look at what is the structure of the derivative, it looks like it's made up of partial derivatives. It looks like in order to get the derivative of v with respect to t, I first took the partial derivative of v with respect to r, and then the derivative of r with respect to t. And then I added to that the partial derivative of v with respect to h, and then the derivative of h with respect to t. And it turns out that this is the way we can compute a derivative in general when I've got a function here, volume, as a function of multiple variables, where each of those variables is a function of another variable, in this case time. And so what we did there was a specific example of what's known as the chain rule. The chain rule says if we have a function of multiple variables, here f of x, y, but we know that both x and y are functions of another variable t, then z is ultimately a function in the end of that variable t, so we can take its derivative. And notice that our notation here, it's dz dt. That's because we're thinking of z as a function of a single variable, that one variable t. So this is just a calculus 1 derivative. It's a derivative of a function of a single variable. But in order to do that, to calculate the derivative of z with respect to t, the chain rule says you can calculate the partial of z with respect to x and multiply by the derivative of x with respect to t, and then add to that the partial of z with respect to y multiplied by dy with respect to t. Let's look at an example of this. So we're going to find dz dt of this particular function. So z is arctan of x squared plus y squared, but x and y are functions of time. So if we use the chain rule, maybe I'll indicate that, I'll say, by the chain rule. To contrast that with, maybe we could do it another way, which we'll check at the end. So by the chain rule, we have dz dt is equal to the partial of z with respect to x times dx dt, plus the partial of z with respect to y, dy dt. And what are those? Well, the partial of z with respect to x, so that's the derivative of the arctangent function, arctan of x squared plus y squared. So if I want to differentiate that with respect to x, then that would be by the chain rule for a function of a single variable, by a chain rule, because it's arctan of some inside function, which we're just thinking of as a function of x. That's what the partial derivative with respect to x means. Just think of it as a function with respect to x and treat the y as a constant. So this would be derivative with respect to x, so that's the arctan is 1 over 1 plus x squared plus y squared squared times the derivative of the inside function with respect to x. That's the derivative of x squared plus y squared with respect to x. That's 2x. And then we multiply that by dx dt. So that's going to be times 2t, because that's the derivative of x with respect to t. So maybe I'll just indicate that that's the part we're doing there, dx dt. And then we add to that the partial derivative with respect to y. So it pretty much has the same form, only it's 2y over 1 plus x squared plus y squared squared times the derivative of y with respect to t. So that's 3t squared. And then we can put it all in terms of t. So let's say maybe I'll put that in a different color just to bring it out. So put in terms of t. Because ultimately z is a function of t, so if we want to find its derivative with respect to t, we might as well write the answer as a function of t. So I'm just going to substitute x equals t squared and y equals t cubed for all those variables x's and y's. So I get a 2x is a 2t squared, and then the other 2t out there becomes a 4t cubed up top. On the bottom for that first term is a 1 plus, and then x squared is a t to the 4th, a y squared is a t to the 6th, and that's all squared. And then we're going to add to that the next term, but they're going to have the same denominator, so I'll just put it here. So 2y is 2t cubed times 3t squared is 6t to the fifth. And so there we go. We've calculated our derivative and we put it in terms of t. Now, I indicated that I said I wrote it by the chain rule and did the chain rule and found the derivative, and that's to contrast it with, we could have done this another way. You know, we could do a check here just to convince ourselves that, hey, yeah, the chain rule, it does give us the derivative. How would I check it? Well, I could say I could just express z as a function of t to begin with. So do the substitution first. X squared is t to the fourth, y squared is t to the sixth, and then we could just do the derivative. So this is just a calculus 1 derivative, a derivative of a function of a single variable. And that becomes a our derivative of arctan 1 over 1 plus the square of the argument times the derivative of the inside function. That would be 4t cubed plus 6t to the fifth. And we see we get the same answer. They're the same. So that's great. So the idea is we introduced this new concept, the chain rule. We did an example with it, and we see that in a case we can actually check, it gives us the same result. Now you may argue that it was probably easier to do it the calculus 1 way, substitute and differentiate. And in this case, yeah, it seems like it probably was easier. But the chain rule turns out to be an extremely useful tool, so we are verifying it in the case that we could check easily the other way, but in general the chain rule will be our go-to in more complicated situations. So let's have a look at the next example. This one we've got 3 variables. So we've got w is arctan of x squared plus y squared plus z squared, where each of x, y, and z are functions of t. We can go ahead and we can compute dw dt, because w is ultimately, in the end, it's a function of t. Now we could do the same technique we did above with the check, just substitute x, y, and z for the t's, and then do the derivative. Or in this case we want to get practice with the chain rule, so let's use the chain rule. So that would be take the partial of w with respect to x, multiply by dx dt. Add to that the partial of w with respect to y, multiplied by dy dt. And then add to that the partial with respect to z, multiplied by dz dt. And the partial with respect to x is, well, it's the arctan again, so it's 1 over 1 plus the argument, or the inside squared, and then multiplied by the derivative of the inside. In this case, that would be 2x, and then multiplied by dx dt, which is 2t. Add to that the derivative with respect to y. So these are, because of symmetry here in our function, these will all look the same, except the top, the variable will just change a little bit. So there's our derivative partial with respect to y times dy dt, so that's 3t squared, plus 2z over 1 plus x squared plus y squared plus z squared, all squared, times the derivative of z with respect to t, which is 4t cubed. And then we can go ahead and substitute in terms of t, so put everything in terms of t. This would be a 2t squared for the x, and then there's another 2t out there, so maybe I'll just go right for the end result. This will be a 4t cubed. And every denominator is the same, so we might as well just write over that common denominator. X squared plus y squared plus z squared squared. Oh, and I wanted those in terms of t. So let's write those in terms of t. I got an x squared, which is a t to the fourth, a y squared, which is a t to the sixth, and a z squared, which is a t to the eighth. And then up in the numerator, we've dealt with the first term. The next term is 2y, 3t squared, or in other words, 6 times y times t squared. So that is 6t to the 5. And then the last one is 2 times 4, which is 8, z times t cubed. So that's 8t to the 7. And there's our final result. And again, we've done it using the chain rule, but you could do your check here in this case. You could do the substitution first and then treat it as a derivative of a single variable function, and you'll get the same result. Okay, so now that's the first chain rule. The next chain rule says that you've got a function of multiple variables. So that's here, function of multiple variables. And each of those individual variables, x, y, and z, are no longer now a function of a single variable t, like they were in the first chain rule we worked at. Now x, y, and z are functions of multiple variables. In this case, we'll say u and v. So our chain rule for several independent variables, the independent variables are the u and v, is the following. What we do is we think of w. Initially, it's a function of x, y, and z, but x, y, and z are all functions of u and v, so w is ultimately, in the end, it's a function of u and v. So it's a multivariable function, a function of two variables. So we can compute partial derivatives of it. We can compute the partial of w with respect to u. And the way we do that is we do our transition through each variable in turn. So I want to compute the derivative of w with respect to u. I compute the derivative of w with respect to its intermediate variable x, and then multiply by dx du. And then I add to that the derivative of w with respect to y, that's the second intermediate variable, and then multiply by dy du, and then do the same thing for the next variable, dw dz times dz du. The key thing to note here is that ultimately we are interested in the partial with respect to u, and in each term that's what we are differentiating the intermediate variable x, y, and z with respect to. Similarly for the next line, if we want the v partial, we differentiate those intermediate variables with respect to v. So let's go ahead and look at an example. We want to find the partials of w with respect to u and w with respect to v, where w is a function, initially it's a function of x and y, but each of x and y are functions of u and v. So w is ultimately, in the end, it's a function of u and v, so we can work out what its u and v partials are. One way you can think about doing this is the same we did before in terms of the check. We'll just take x equals u squared plus v squared, plug it in for x, take y equals u squared minus v squared, plug it in for y, and then we just get w as arctan of u squared plus v squared over u squared minus v squared. So that's a function of two variables, and you can go ahead and differentiate it. The idea with the chain rule is to sort of split those things apart. It's saying, you know, you got an outer function, it's the arctan, and it's involving this ratio of x over y, so we'll deal with that on its own. And then we will deal with the fact that x and y's are functions of u and v on their own. So we can do those derivatives independently and then piece them together with the chain rule. So the chain rule makes it easier to sort of compartmentalize calculations and then bring them all together. So here's what we'll do. We'll take the derivative with respect to u, and we'll do it with the chain rule. So that says take the derivative with respect to the first variable x, and then multiply by the partial of x with respect to u. And then add to that the derivative of the outside variable w with respect to the next intermediate variable y times dy du. And dw dx, so this is the derivative of arctan x over y with respect to x. So that's 1 over 1 plus x over y all squared times the derivative of the inside, the x over y, with respect to x. So we're just thinking of this as a function of a single variable, x, where y is a constant. That's the idea of taking these partial derivatives. So I need to take the derivative of x over y with respect to x. So that becomes a 1 over y. So I'll just put that up top here. That's a 1 over y, or the derivative of the inside function of arctan of x over y with respect to x. And then I need to multiply by the derivative of x with respect to u. So that becomes a 2u. Then we can go on to the next term, dw dy. So that is 1 over 1 plus x over y all squared. Again, that's the arctan, the derivative of the arctan part, Now I need to multiply by the derivative of the inside. The inside is x over y. I'm differentiating it with respect to y. So x over y, the x I'm treating as a constant, so it's just what is the derivative of 1 over y? That's a negative 1 over y squared. So we have a negative x over y squared. That's the derivative of the inside function. And then we multiply by dy du, which is 2u. And then we can go ahead and put everything in terms of u and v. So we've got our 1 over u squared minus v squared up top. I've got a 1 plus u squared plus v squared over u squared minus v squared squared on the bottom, multiplied by a 2u plus a negative x is now u squared plus v squared, so put those in parentheses, all over y squared, which is a u squared minus v squared squared, and that's all over 1 plus u squared plus v squared over u squared minus v squared all squared, and that's multiplied by 2u. So you can do a bit of cleanup. If we needed to do something with this, we'd simplify it algebraically, but we're just asked for the derivative. We're not doing anything with it at this point, so we can leave it in this unsimplified form. The next one, we're interested in the partial derivative with respect to v. So again, by the chain rule, it's dw dx dx dv plus dw dy dy dv. So the partial derivatives, w with respect to x, w with respect to y, those are the same. So we have the same thing as we did above, 1 over y, 1 plus x over y all squared, times, and then it's that point, the dx dv, where things change a little bit. So this is now a 2v, rather than above where it was the partial with respect to u, which was a 2u. And then we add to that the partial of w with respect to y, which we've already worked out above, and then we multiply by the partial of y with respect to v, so that's a negative 2v. And then we could plug in terms of u and v, and we don't get much insight there, so I'll just indicate put in terms of u and v. In other words, take all the x's and y's and just write what they are in terms of u and v. So those are a couple of illustrations of the chain rule as applied to functions of a multiple variables, where each of the variables are themselves functions of multiple variables. Let's have a look at another example. So suppose we have w is a function of u, v, x, and y. So it's now a function of 4 variables. But this is that u and v are functions of x and y. So that's a function of x and y, and that's also a function of x and y. So ultimately, w is really a function of x and y alone, but maybe in the context of the example, it was appropriate to split them up in this way, to look at w as a function of some combination of x and y's, another combination of x and y's, and then just the remaining x and y's sort of floating around. So we grouped some x's and y's together as a u, some x's and y's together as a v, and left the remaining ones as just x and y. So whatever the case, however this came about, we're interested in finding the partial derivative of w with respect to x and w with respect to y, because ultimately w is just a function of x and y. So one thing to keep in mind here is that when we're looking at x's and y's, these are independent. It means that x is not going to be a function of y and y is not going to be a function of x. They are two completely independent variables. This is the nature of how we've been dealing with them in multivariable calculus. Our inputs to our functions are we've got an x-axis, we've got a y-axis, and our points are somewhere in the xy plane. And then our z value depends on those. So our z value depends, or is a dependent variable, whereas x and y are independent. So what this means is that y is not changing because x is changing, and x is not changing because y is changing. They are independent of each other. we change them however we want independently. That's going to come into play here, and we'll see why. So what are we interested in? We're interested in del w, del x, or dw dx. And so let's use the chain rule. What is the derivative of w with respect to x? Well, it's the derivative of the function f with respect to u times du dx, because that's the first variable that f is expressed in terms of, plus, then I need to do the derivative with respect to the next variable, and then the derivative of that variable with respect to x, plus the derivative of f with respect to the next variable, times the derivative of that variable with respect to x, plus the derivative of f with respect to the final variable, times the derivative of that final variable with respect to x. And there's a couple of key observations to make here. Dx dx, well, what's the derivative of x with respect to x? That's just 1. Dy dx, what's the derivative of y with respect to x? Well, I think of y and x as independent variables. So in some sense, y is constant relative to x, right? I mean, if we're thinking about differentiating, doing a partial derivative, we treat all the variables as constant except for the one that we're differentiating with respect to. So here, this would be 0. And so this becomes df du dx plus df dv dx plus df dx. And so there is our partial of w with respect to x. It's made up of those partial derivatives put together in that way by the chain rule. The second example is asking for dw dy. Take a moment, pause the video, try to work this one out for yourself. Very similar pattern to what we had above because it's just the chain rule that I'm applying. So pause the video and try it out for yourselves. Okay, let's work this one out. dw dy. That is df du du dy plus df dv dv dy plus df dx dx dy plus df dy dy dy. Okay, so that's the chain rule. Dx dy is 0, dy is 1, and so this becomes df du du dy plus df dv dv dy plus df dy. And that's our partial derivative of w with respect to y. Okay, so that brings us to the end of the first half of the video lecture. So we have covered chain rule, where we've got a function of multiple variables and each variable is a function of a single variable t. And then we've looked at the chain rule where we've got a function of multiple variables and each of those variables is itself, again, a function of multiple variables. What we're going to do in the second part of this lecture is we're going to look at implicit differentiation, so the analog of implicit differentiation from Calculus 1. So this idea of if we've got a surface described by an equation, such as a sphere, x squared plus y squared plus z squared equals 1, how we can do implicit partial differentiation using the chain rule. And then we'll also look at some more additional examples of using the chain rule just to get these ideas nice and solid. All right, thanks for watching, and we'll see you in the next lecture.